guys. All right. Still over here. We're gonna pick up with where we left off last lecture. Okay, so this is Friday, March 27th lecture, video 1. Okay, so we've done some ice table questions. And we've done some calculations of K, right? So we calculated K in the sense that we knew all of the equilibrium concentrations, so it was just a plug and chug into the K expression. We calculated K from the sense that we knew all of the initial concentrations and one of the equilibrium concentrations. So if you know initial and equilibrium for the same thing, you can then figure out the change. Then we could use stoichiometry, figure out the changes for the other guys, and then I plus C equals E. Now we have all the equilibrium concentrations, and we can finally plug and chug into the K expression. The last thing we really talked about last lecture was comparing K to Q, where Q is essentially the same exact thing as K. It's just that K means that we're at equilibrium and Q means we could be anywhere, right? So Q could equal K and mean we're at equilibrium, or Q could be greater than K or less than K and mean that we're not at equilibrium and help us figure out which way we're going to move to get to equilibrium. Okay, so what I want to focus on now is how do you calculate equilibrium concentrations if you don't know any? So how can we figure out, so in the previous example, we knew all the initial and one equilibrium and we could figure out K. So what we're going to talk about now is let's flip that. So we're still going to start with we know all the initial, but what if instead of knowing one equilibrium and not knowing K, what if we knew K, but we didn't know any of the equilibriums? You can figure them out as long as you know K. If you only know the initial concentrations, you can't figure anything out. You can't figure out the equilibriums or K. I mean, you could set up some sort of a weird algebraic equation to represent it, but that's not what we're talking about here. What we're talking about is you still know the same number of items. It's just that we're changing what that item is, right? Instead of now knowing an equilibrium concentration, we're going to instead know the K. Okay? So, but here's the deal. If you don't know any equilibrium concentrations, think about the examples we did last class. If you know a numerical value for I and you know a numerical value for E, then we were able to figure out a numerical value for C. But if you don't know a numerical value for E, you don't have any equilibrium concentrations, then there's no way to figure out a numerical value for C. You can't have a numerical change, which means we need to use a variable. Now, I'm going to use X because in the rules of algebra, X is just the most common thing to use. Okay, but don't get too bent out of shape about the fact that it's an X. It could be anything, right? Any variable. Now, stoichiometry still matters. And it matters if we are losing something or gaining something. So if we started with an initial concentration of something, then that X is going to be negative, right? We're losing. If we didn't start with an initial concentration of something, then its X is going to be positive. But then you also have to look at the coefficients because it could be like a negative 2x or a positive 3x. We're going to work through an example on how to do that, okay? And this is basically everything that I just said, all right? So we're going to talk and work through an example together on how we can actually solve this. And I'm going to do it through the slide, and then I'll work out one for you on a piece of paper. Okay? All right. So let's move forward. So the annoying thing is, though, before we move forward, let me hover on this last statement that appeared. You are going to have to solve the quadratic formula to determine X. Now, I'll show you how in a second, all right? But you're going to have to use the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac over 2a. You may be singing the song in your head, and that's cool. I'm assuming. So you should have had at least Algebra 1 before you took chemistry. So the assumption is, from me, that you know what the quadratic formula is and you know how to solve it. Okay, so I'm not really going to spend a lot of time going over that because I assume that you can do it. If you have any issues, you need to talk to me about that in the office hours discussions or send me an email, all right? Okay, so let's work through an example together. So it says a 1-liter flask is filled with 1 mole of hydrogen gas, 2 moles of iodine gas at 448 degrees Celsius. The value of Kc at this temperature is 50.5. What are the equilibrium concentrations of both of those two things we talked about, the two reactants we're starting with amounts of, and the product, HI, which we're not starting with anything of? Okay, so the first thing we need to know is we need to tabulate everything we know. So we need to write down everything that we know. So we're going to set up our ice table and we're going to start plugging it in. Right now, molarity equals moles over liters. In this case, since liters is 1, dividing by 1 doesn't change anything. So our initial concentration of hydrogen is then going to be 1. The initial concentration of iodine will be 2. And since they didn't mention having an initial concentration of HI, we assume we have nothing. Right? Now, there's nothing else to write here. There's nothing else we can put in our ice table, so we just have to move on. Okay? But now we can determine C. Okay? And how we're going to determine C is we're going to call our change X for everybody, right? But if you start with an amount of something, that's going to be a negative X. So for H2 and I2, those are going to be negative X's. For HI, that's going to be a positive X. We also have to account for the coefficient, okay? So we started with something, so this is going to be a negative. The coefficient is 1, so this is going to be a negative X, okay? Started with something, so it's going to be a negative. The coefficient is 1, so negative X. So the change is the same here. But this, we started with nothing. So this is going to be a positive. A positive what? 2. Now I have a coefficient, X. Okay? And then I plus C equals E. So the equilibrium concentration of H2 is 1 minus X. The equilibrium concentration of I2 is 2 minus X. And the equilibrium concentration of HI is just 2x, right? Because 0 plus 2x is 2x. Now, at this point, you still may not be seeing how we're going to be using the quadratic, but hang on, because I promise you, you will see it on the next slide, okay? But everything we've done so far is just filling out our ice table. Now, what we need to do is we need to write our K expression, okay? So it's going to be the concentration of HI squared divided by the concentration of I2 divided by the concentration of H2, and I know what that's equal to, right? It's equal to 50.5. Okay? Always write the expression before you start plugging stuff in. Why am I saying that? Because you're going to forget about sort of squaring things and things like that if you don't. So write the expression first. All right, now we're going to plug in. Okay, so for HI, it's going to be 2x. So that's 2x squared on the top. And then I'm going to plug in. So for H2, it's 1 minus x. And for I2, it's 2 minus x. And maybe now you're starting to see the problem, right? Because when you FOIL, right, I'm assuming you know what the word FOIL is. When you FOIL these two parentheses, so 1 times 2, 1 times negative x, and then negative x times 2, and negative x times negative x, and you smash it all together, that's what FOILing is. You're going to end up with an x squared, an x, and a number. And the only way to solve an x squared, an x, and a number is to use the quadratic. So let's figure out how we're going to rearrange, right? If this was me, the first thing I would do is I would cross multiply. So I would multiply the 50.5 times the 1 minus x times 2 minus x, okay, just like this. And then 2x squared, that's an easy thing. Just go ahead and do it. 2 squared is 4, and then it's going to be x squared. Now, before you distribute, personally me, I would go ahead and FOIL this, right? So just like I said before, 1 times 2, 1 times negative x times 2, negative x times negative x, and that comes out to, so negative x times negative x is x squared, and then you had a minus 2x and a minus 1x, so when you add those together, that's a minus 3x, and then 1 times 2 is 2. So here's what we get from FOILing, okay, and this is still equal to the 4x squared, right? I'm just choosing not to rewrite it. Now at this point, I would distribute this 50.5, so 50.5 times x squared, 50.5 times -3, 50.5 times 2. Okay, so distribute that 50.5 into that parentheses. But then this, to use the quadratic, this needs to be equal to 0. And right now it's not equal to 0. All of this is equal to 4x squared. So if we want to get this to be a 0, I need to subtract 4x squared from both sides. 50.5 minus 4 is 46.5. So I end up with 46.5 x squared minus 151.5x plus 101 equals 0. Now I can use the quadratic formula. Okay? And as I said before, I'm assuming you know this, but the quadratic formula is negative b plus or minus the square root of b squared minus 4ac divided by 2a. And if we go back to this equation, remember a is the number associated with x squared, so a is 46.5. B is the number associated with the x, so negative 151.5. And C is just the number, so positive 101. So the next thing you would do, so here's your negative, and then your b is actually negative, so this becomes positive, plus or minus the square root of the negative squared is going to become positive, minus 4 times AC divided by 2a. Now here's the deal. Remember, the plus or minus means you're going to end up with two numbers here, right? I'm not going to talk about really solving the quadratic because, again, I assume that you can do this. But remember, you're going to end up with two numbers. Now, I promise you, my promise to you is this. One of those numbers will not make a hill of beans sense. What do I mean by that? These are the two solutions for x. One of them will work, one of them can't. Well, think about it. The highest initial concentration you had was 2. Can you lose more than you started with? Absolutely not, right? So the only one that makes sense is the 0.935, right? Because I cannot lose more than what I started with. So at this point, I now have a numerical value for x, so I am a lot closer. All I have to do is I have to go back to my ice table at this point, plug in that 0.935 for x. So this was originally a negative x, so now it's going to be negative 0.935. This was originally a negative x, so it's going to be negative 0.935. This was originally a positive x, and if I say 2 times 0.935 in my calculator, this is going to end up being, this right here, this change for HI is going to be positive 1.87. Okay? And then you just I plus C equals E. 1 minus 0.935 is 0.065. 2 minus 0.935 is 1.065. And then this one's straightforward, no calculator needed. 0 plus 1.87 is 1.87. Now, let me be clear. These are all concentrations. So this is 0.065 molar, 1.065 molar, 1.87 molar, right? All of these should have a molarity unit after them. How can you check your work? Okay, how you can check your work is you should be able to take these equilibrium concentrations, put them into your K expression, and get the K that you were originally given in the question. If you plug these numbers back into your K expression and you do not get this number, you have made a mistake somewhere, okay, in your algebra. The hardest thing about these questions is really it's the algebra associated with using the quadratic formula, okay? Now, there's another example here in the slide. I'm not going to work through this one with you, but you have it for your notes, okay? And those answers are correct. In this case, notice the units are not molarity, they're pressures, because the original unit was an atmosphere. Your equilibrium concentration should be the same as your initial as far as units. Okay? All right. So this is the end of video 1. I will see you in video 2. Stover out.